Okay, welcome to Ball on Flat Ground video. So we're going to dive right into the experimental setup. The experimental setup involves 3 stopwatches and a ball bearing and our PVC ramps. Now we're going to have about a third of the class do a low ramp. I just use this chair. Another third do a little bit higher. And then a final third do this higher part. And I like this higher part because I use it in all 3 of the experiments in this unit. Ball on flat ground, ball on ramp, and height versus final velocity. It's what I use for my predictions. Now it's fast, so you have to have a good group of experimenters take data with this. For a ball on flat ground, we're just going to let it roll down the ramp so it comes off at the same speed every time. We give it 1 meter to stop bouncing, and then it rolls to the starting line. That's where you start. And then I have my groups. The first time I ran this was a group of 8. So 3 of them were timers. Start, stop, all 3. Then they roll it again. The 3 timers start it and stop, and so on until they get all 3 by 5 data points. Then they're going to go to Logger Pro and of course get a proportional fit. Big error bars will make sure that happens. If they still can't get it with big error bars, they need to retake their data. So one other eye on the prize comment for the board meeting is that we want to move them from experience to the graph to a mathematical understanding. What do I mean by that? So during the board meeting, they're going to notice that all of them are linear, but they have different slopes. Oh, and the ones with the steepest slope are the ones that have the ramps with the highest ramp height. And that's very intuitive that they see that connection, and then it's another intuitive step to say, what's different about a ball bearing coming off a high ramp versus a low ramp? The starting speed. So now we have them intuitively making the connection that slope is related to speed. And then with unit analysis, we can enforce that and see that it's meters per second. So again, we move them from an intuitive experience to a graphical understanding to finally a formula. Then later we're going to do the prediction. One fun thing to do is have half the class stand at the wild guess, and then you have the other 20 or so students stand at the data-informed prediction, because it's great, because the ball just rolls past all the wild guess people, and then there's the clump of data-informed. So even if it's not down to the centimeter right, it's in that clump, and it's very clear that the data-informed people were right on, and the wild guess people were far off. And then taking it to problem solving, making it last. So we want to reinforce this throughout the course, that formulas are a shorthand for connecting past empirical observations, this lab, to the current problem. So when they have some problem that involves constant velocity, asking for some time, we want to bring them back. And the way I do it is I have my 4 patterns on the wall, and then I have the 4 patterns applied to the unit, motion patterns right here. And so if the question was asking about time, I would always start with the graph. Okay, with constant velocity, we know there's a constant slope. It went 60 meters. What time? Well, we just got to go over 60 till we find out for that slope, come down, and find the time. If we don't have the graph, then we'll use the mathematical representation, but I'm still going to bring them back to the ramp lab, talk them through the graph, and bring up the mathematical formula, and use it as needed. All right, thank you.